let's stop talking about Taylor series and let's find one. So I've got the sine function, and I want to find the Taylor series for sine when it's centered at -4. So I have to do a few things. The first thing I need to do is go ahead and just write out the definition of a Taylor series. We say that so the sine function is going to be equal to, so if this is f of x, then it's going to be the nth derivative at c divided by n factorial times x minus c to the n. So remember, this is a power series, so we have x minus c to the n. And then all these are always going to resolve to some number, right? The idea here is that this is not really a function. Even though you see this f, we're actually evaluating it at a point, so we get a number. So the real trick here, this is easy, right? We can plug this in all day. This is the hard part. So we have to kind of figure out how in the world are we going to get that? Well, the way we do that is by writing out a few terms, seeing if we can't notice a pattern. So C again is -pi/4. One thing that you might, some helpful tips and tricks. One is that sine of pi/4 is actually the same as cosine of pi/4, which is 1 over the square root of 2. So, right, remember that's a unit circle value there. These actually have the same value. Now, we also know that sine is an even function, or an odd function, I apologize, which means that sine of -pi/4 is the same as negative sine of pi/4. So that means an odd function, you can kind of pull the negative out front, and so that's -1 over square root of 2. And cosine is an even function. What does that mean? It means it sort of eats the negative. What it means, if you were to look at the graph, even functions look the same on the left side and the right side of the graph, which means if you're plugging in a negative value, it's just like plugging in a positive value. But odd functions, if you were to graph them, when you plot positive functions, or positive value, or positive inputs of the function, and you plot negative inputs of the function, they have the opposite. So if it was positive when you plug in a positive, it's negative when you plug in a negative. If it's negative when you plug in a positive, it's positive when you plug in a negative. So the idea is it has this sort of opposite behavior, but the sort of the nice piece about it is you can think of it as sort of extracting the negative. It's in this sort of eating the negative. That's at least how I envision it. Kind of helps keep me straight here. So these are going to be helpful because we're going to use them in this. And I'm going to do a little bit of a trick here, something that you wouldn't really know unless you did a lot of work. So I'm going to give you a little hint here, and that is that there's a pattern. So if I have a pattern that looks like this, so I have this specific 4 sequence, then I can model this pattern by that particular pattern. -1 to that pattern. You can think about this where this is the 0th term, first, second, third, fourth, and so on. If you plug in 0 here, you're going to see it's 2 times 3 over 2. So that's 6 over 2, that's 3. So -1 to the third is this. If you plug 1 in here, you get 3 times 4 over 2. That's to the 6th power. -1 to a positive number is 1. And if you keep plugging in, you're going to see this pattern produce these coefficients. Why is that important? You're going to definitely see why that's important in a minute. So that was a little bit of me doing some upfront work that I don't normally do and definitely needed to do here, or we'd have been here a long time. Alright, so anyway, let's continue on with the theory, right? So the idea behind what we want to do here is we need to find this pattern. So we've got to generate a bunch of terms. We have to say, okay, well, Well, that sure didn't work, did it? Maybe this one will. Ha! That didn't work either, did it? Oh my goodness. Alright. Alright, let's hope. Alright, so the function is sine of x. That's sort of like the 0th derivative, because that means there's no derivatives applied. So this is the first derivative, the second, the third, the fourth derivative. Now, oh man, this marker's already dying. Maybe I'll get another one real quick, real quick. Let's try this one. My goodness. So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine is positive sine. Now, hopefully you've noticed that we started here, and the same derivative's there. So what do you think the fifth derivative is? Now, I mean, you could do it manually, but you should notice that if I started here, I've already got the derivative of this function. It's here. And then you can keep on going if you needed to. Why is that helpful? What that tells me is that every 4 terms, it's going to repeat. The derivative's going to repeat. Oh, okay. So I have this sort of periodic derivative behavior. So then if I do my function at c, I get sine of negative pi over 4. Sine of negative pi over 4 is negative 1 over square root of 2. The first derivative, cosine of negative pi over 4, is 1 over square root of 2. So let's write that as negative 1, positive 1. So negative sine of negative pi over 4 is actually going to be a positive 1 over square root of 2, because those negatives are going to cancel each other, because I'm going to pull the negative out, and the negative that was already on the sign is going to cancel. So then when I take the third derivative, I have negative cosine. So it's the negative version of the positive cosine. So I get negative 1 times 1 over square root of 2. And then, when lo and behold, I start over, I get negative 1 times 1 over square root of 2. And then I get 1 times 1 over square root of 2. So what do I notice here? What do I notice? I notice that in each particular case, I always have a 1 over square root of 2. Right? And that doesn't change at all. But what I also notice is that I have these coefficients, these negative 1s and positive 1s, right? I have a negative 1, 1, 1, negative 1, okay? So negative 1's on the outside, 1's on the inside. Negative 1, 1, and then you would see a 1, negative 1, right? You'd see, oh, maybe this pattern is what you would see. Oh, haha, right? So instead, what I can do is I can say, I see that I always have a 1 over square root of 2. Always have that. So if I always have that, then I have a 1 over square root of 2. But then the other pattern is n plus 2, n plus 3 over 2. So do yourself a favor, right? Try to plug in 0 here and resolve this and see if you can't replicate this exact list going from 0 to 5. You should get this exactly, no problem. But remember, when we're trying to set up a Taylor series, we need to also divide it by n factorial. So this becomes something that looks like that. So what we end up with is simply that sine of x is n equals 0 to infinity, 1 over square root of 2 negative 1 to the n plus 2, n plus 3 over 2 over n factorial times x. So remember, this is x minus c. X minus c. But our c is already negative. So we actually end up with x plus pi over 4 to the n. And that is an expansion. Now, that's not the canonical expansion. The canonical expansion of sine is actually a lot simpler if the center is 0. This problem becomes significantly easier when n is equal to 0. But the key is to try to show it that you can do it really with any center. If you didn't do it with something convenient like these unit circle type values, you'd be in for a world of hurt, so I wouldn't recommend it. But I would always recommend trying to pick unit circle values if you can. But this is sort of the trade-off in practical applications. You may not always have that luxury.